So today's warm-up question. Says, when a baseball bat strikes a baseball, which experiences a greater force? And we're going to be talking about the answer to this today. Guys, y'all listen up. We're going to be talking about this today because it's part of Newton's third law, which is the topic of our notes today. We're also going to bring back in kinematics, which was in the notes that you were looking at 2 days ago and maybe even yesterday after the PSAT. But the answer to this question, actually, does anybody know which one experiences a greater force? Yes, sir.
Neither.
Yeah, the answer is that it's the same. Okay, the forces are equal and opposite to each other. And that seems a little counterintuitive because you look at the scenario and you're like, well, the baseball just rockets off the bat at like a crazy high speed and the bat doesn't seem to be affected as much. There are other forces at play, but for the interaction between those two objects specifically, this is Newton's third law. Okay, and I'm going to give you a definition for that in a minute. But your answer to the warm-up question is the force on the bat is equal in magnitude to the force on the ball. And I know we haven't talked about it yet, so if you're like, what? That's weird. That's okay, but you're going to want to mark it for your warm-up. So what does Newton's third law say? You have heard it before, I promise. It says, for every action, there is an equal and opposite reaction. Okay, that is Newton's third law. Because forces are interactions between two objects, Isaac Newton referred to these forces as action-reaction force pairs. And so when we talk about the interaction between these objects, we're going to start talking about these pairs of forces, the action force and the reaction force. And yes, they will be equal and opposite to each other. That's what Newton's third law says. And there are a lot of misconceptions regarding Newton's third law. So you better believe you're going to see it on the test, and you're going to see it in ways that are designed to trick you, where the motion of the objects is very different afterward, like the baseball and the bat. Okay, but you need to remember, hey, that's a force pair. Okay, and so it's going to be equal and opposite. For every action, there's an equal and opposite reaction. What this means is the force exerted on one object will cause a force of equal magnitude but opposite in direction on the other object in the interaction. So if you want to write it out in more words, there you go. That's saying the same thing, though. Okay, that's the exact same thing that we just said. But when you have a force that's exerted between these two objects, the force of one object on the other will be equal in magnitude but opposite in direction compared to the force of the other object in the interaction. So again, they're going to be equal and opposite. We're going to look at a lot of examples today. Okay, so we have looked at representations of forces previously in something called a free body diagram. So we were able to represent the forces that act on an object with a free body diagram. For example, here is at least one of the forces acting on the ball. Technically, if I wanted to make this a more accurate free body diagram, I would also include FG, but right now I'm just going to focus on the bat and the ball. Okay, and so if I look at the free body diagram for the ball, I know that the bat is going to apply a force to the ball that is to the left. I can see it in the image right there. When he hits it, I know it's going to push it to the left. But you can't see the force pair in a free body diagram. So these diagrams that we've been drawing throughout this unit and actually starting in last unit only show the forces on one object, which means you can't see a force pair. You would have to draw a second free body diagram like that one. And so now you have these two different objects. You have a diagram for the ball, you have a diagram for the bat, and you can see that if you look at the two diagrams together, you can see the force pair, because here's the force of the bat on the ball going to the left, and here's the force of the ball applied to the bat going to the right. And we will use these equivalence marks, the same thing that you use in geometry, the little hash mark to show that something is equivalent. You use them on like sides of triangles or on angles, or you can do two hashes, whatever, but make sure that they're both the same. So either one on both or two on both. But anyway, this is your force pair. Okay, again, you'd have to draw two different free body diagrams to see it, which we don't typically do. Usually we're focused on one object with a free body diagram. So we're going to talk about another type of diagram, but first let's talk about identifying these force pairs. So you're going to be given a series of scenarios like this one. A book is at rest on the table, and when you look at the scenario, you need to identify what two objects are interacting. This one's pretty obvious. Book, table. It's in the sentence. Okay, and so we have two objects, book and table. And then you're going to write out your force pairs. Okay, your force pairs are going to be written like this. The book pushes down on the table. Okay, and then when you write the other half of that, you're going to have the exact same two objects, table and book. You're going to flip the order. So instead of book pushes down, you're going to have table pushes up. Equal and opposite. Table pushes up on the book. Okay, so that's the force pair. Okay, the book pushes down on the table pushes up on the book. Again, you could come up with a force pair for an interaction between any two objects. It doesn't have to be a book and a table. It can be the baseball and the bat. It could be you and the earth. Okay, whatever it is, you should be able to write out a force pair for it. Okay, now those are kind of wordy, so you can, again, show that they're equal and opposite. This is a little shorter. Force of table on book equals force of book on table, equal in magnitude anyway. You'll notice there's a negative sign here because they're opposite. But that's still kind of long to write out. So you could write it like this. Okay, this is more of a shorthand. Force of table on book. When you read it, it's literally table on the book. Okay, it's like sitting on top of the word book. And then this is the force of the book on the table. Since the book is pushing down on the table, that one has a negative sign in front of it. Because the table is pushing up on the book, that one is a positive force. But again, that's your force pair. So you could write it like that. Okay, and so you'd have these two forces showing that they're equal and opposite. Now I said that we can't see these in a free body diagram, because if you were to, again, look at the free body diagram for the force acting on the book. Okay, I know that one of these in my force pair is acting on the book. This is the force of the table on the book. It's an upward force. Technically, that's my normal force. I could even be more precise. Normal force. Okay, and the other force acting on my book, gravity, because it's on Earth. Okay, and so I have these forces, and those are the only forces that I would need to draw if I was diagramming the forces acting on a book that's sitting at rest on a table. That's it. F, G, and Fn. And because it's sitting at rest on the table, I would draw it so that Fn and Fg are equal in magnitude, because I want my net force to be 0 because my book is at rest. It's not accelerating. So we're drawing it that way on purpose. Okay, which leads to a misconception. Are Fg and Fn a force pair? They are equal and opposite, but are they a force pair? And the answer is no. That's one of the most common misconceptions. Okay, the force pair is over here. The force of the table on the book and the force of the book on the table. You can't see the force pair in the free body diagram. Yes, Fg and Fn are equal and opposite, but they're not a force pair because they're not an interaction between the same two objects. Fn is between the book and the table. Fg is between the book and the earth. So what do we do when we have this third object, or really planet, thrown in there? Okay, how do we diagram all of these other forces that aren't showing up in here? And but again, let me read this first. Fn is a force between the book and the table. Fg is a force between the book and the earth. Again, we just said that, which means this interaction, yes, we're focused on the book and the table, but there are other things that we could also focus on. Okay, and we can represent the forces between all of these objects, including the earth, if we want to include it. We could make this thing endlessly complicated. We're not going to. We're just going to include book, table, earth. Okay, but we can represent the forces that exist between these objects with something called a schema. Okay, so you can see a schema up on my screen right now. A schema shows all force pairs between multiple objects in a scenario. The free body diagram that we drew just a moment ago only shows the forces on one object, and we can't see force pairs. So if you want to see force pairs, you have to draw a schema. Okay, so here is an example of a schema. When you draw the schema, you're going to simply label the objects that are in the interaction that you're looking at. I've got 3. Put them in circles, so book, table, earth, and then you're going to use double-sided arrows between each of them, and those double-sided arrows represent the force pair because, again, the force is between the two objects, and you have an action and a reaction force. Okay, so if I were to take a look at each of these, this is the one we already looked at, the force of the table on the book and the force of the book on the table. That's one force pair. It is represented by my blue arrow. But I could also look at this red arrow. And this red arrow is between the table and the earth. And this is the force of the table on the earth and the force of the earth on the table. The table's not floating away because earth has a gravitational field. And so the earth pulls down on the table. And in turn, the table pulls up on the earth because their gravitational fields overlap. And yes, that's weird. But the same thing's true for you. The earth pulls down on you, and the other half of that force pair is you pull up on the earth. Again, sounds weird, but that's the other half of the force pair. Any two objects with mass will attract each other gravitationally. Okay, even you. All right, and then we have this green one, book and earth. Same thing. This is going to be a gravitational force between the book and the earth. The force of the book on the earth equals the force of the earth on the book. Since the earth pulls down, that's why that one has the negative sign in front of it. But again, they will be equal and opposite to each other. All right, so this is a schema. A schema, again, shows your force pairs. So you can't see them in a free body diagram. So if you're looking at a free body diagram and there's a question that says, are these two things a force pair? Your answer will always be no, because you can't see a force pair in a free body diagram. All right, here's my force pair. It's highlighted in yellow. Table pushes up on the book, and here's the other half of it. Oh, that one's earth pulls down on the book. Sorry, that's not the other half of it. That's the free body diagram. I apologize. These are the forces on the book. Okay, so here are my forces on the book. There's only two. When I read each of those force pair statements, only two of those things are happening to the book. The table pushes up on the book, the earth pulls down on the book. So again, you can go from a schema to a free body diagram. You could go the other way around. But again, the schema shows all the forces between multiple objects in the interaction. The free body diagram focuses on one object. So we've already drawn this one.
Ms. Starling?
Yeah.
How could you go from a free body diagram to a schema?
You really can't go directly. It'd be hard to do. But like when you draw the free body diagram and you see that normal force, you know then that there's an interaction between the book and the table. And then when you draw FG, you know that you need to include the earth as well. So it would kind of give you a hint as to what to include.
Okay.
Yes, sir.
Coach Pete has rulers.
He did.
What are you
Right there.
doing here?
I'm coming some rulers.
All right. So again, schema, free body diagram. I'll tell you right now, schemas, they don't really show up on your test. We will ask you about force pairs, but I'm not going to ask you to draw a schema. Okay, a schema is just a tool that helps us see force pairs. So we don't really test you over them or really ask you a whole lot of questions. But if you're struggling in identifying the force pairs, or if you're falling for that misconception thinking Fn and Fg are a force pair, the schema helps to illustrate why they're not a force pair. Okay, so again, you really don't see these on a test, but they are a helpful tool for identifying each of these sets of force pairs. All right, so again, we've already talked about Newton's third law, and it does lead us to the misconception that I've already mentioned. For every action, there's an equal and opposite reaction. Right now, the earth is pulling down on you. That makes you have your weight. You can calculate it. Fg equals m times g. Okay, if we call that the action force, then what would the reaction force be? If every action has an equal and opposite reaction and the earth is pulling down on you, what's the other half of that? And I mentioned this one a second ago.
You pulling up on the earth.
You pull up on the earth. Yeah. Okay, and so that's the other part of it. It's not the normal force from the floor. This clip is silly, but